In this video, we'll be dividing radicals. Just like we have product rule for radicals, we have quotient rule for radicals. And quotient rule says that if you have a quotient underneath of a radical, you can break it up into the nth root of the numerator over the nth root of the denominator. So let's divide the square root of 50x to the third by the square root of 2x. We're actually going to be using quotient rule kind of backwards. We can go either direction with these rules. And we are going to rewrite this as the square root of the fraction. How do I know that I want to do this? Because I don't have any perfects underneath of my square roots. That's what we're trying to get to. We want to have something nice that's going to simplify for us. Since we don't, I'm going to see if I put it together as a single fraction and simplify the fraction if I end up getting something nicer. So let's simplify what we have underneath of our square root now. 50 divided by 2, that's 25. A to the third divided by a to the first. I'm going to subtract my exponents and get x squared on top. Well, how nice. I now have two perfects underneath of my square root. The square root of 25 is 5. The square root of x squared is just x. Now we're going to see in our subsequent examples that everything doesn't always turn into a perfect, but hopefully something's going to simplify. In our next example, we have the cube root of 125 a to the third b to the fourth over 27. So I look at the fraction that I have inside my radical and see, can I simplify that? There's no number that divides into 125 or 27. So that tells me that I should try to break it up into the cube root of the numerator over the cube root of the denominator. Also, looking at this problem, it jumps out at me that 125 and 27 are both perfect cubes. So that's kind of a giveaway that we would want to break it up as well. So the cube root of 125, a to the third, b to the fourth over the cube root of 27. So let's simplify our numerator. You may want to break it into 2 as we have before. Cube root of 125, cube root of a to the third, b to the fourth. So the cube root of 125, well, that's a perfect. That's just going to be 5. 3 divides into 3 one time, so that's a to the first on the outside with no remainder. 3 divides into 4 one time, b to the first on the outside with a remainder of 1, so b to the first underneath. And then we simplify the cube root of 27. That's a perfect. It's 3. We end up with 5ab cube root of b divided by 3. Next, we want to divide the square root of 60a to the fifth b over the square root of 12ab to the third. Now, at quick glance, I don't see any perfects underneath of either square root. So that tells me maybe I should try to make it the square root of one fraction and simplify that fraction. So this is the square root of 60a to the fifth b over 12ab to the third. So let's see what we can do to simplify underneath. 60 and 12 are both divisible by 12, so this is going to give me just 5. And now I have a to the fifth divided by a to the first. That's going to give me a to the fourth on top. And then we have b divided by b to the third. That gives me b squared on bottom. Great. So I see these exponents of 2 and 4. I have an index of 2. I want to simplify those. So now we're going to apply quotient rule a second time and break this up into the square root of the numerator over the square root of the denominator and simplify. As we did in the previous example, you may want to look at the numbers separate from the variables. The square root of 5, there's no perfect that's a factor of that, so that's just going to stay the square root of 5. But with the square root of a to the 4th, our index of 2, 2 goes into 4 2 times, so that's a to the 2nd on the outside, with no remainder, so we have no a's underneath of our radical. And then simplifying the square root of b squared, 2 goes into 2 one time, with no remainder, we get a final answer of a squared square root of 5 over b.